And you can see that and some weird countdown timer. Now I just need to find my screen. All right, let me back out of this and try this again. So much for a smooth transition, right?
You can blame me. I'm still blamed for a lot of things at Savannah River for distracting you.
No.
Or just blame you, Kevin, for anything.
Well, we're also giving more people a chance to hop in, right? I just need to figure out how to get this full screen. There we go. Okay, so hopefully that works, and I'll try not to reflexively wave my pointer all over the place, just like I would in real life. Yeah, so the title of my talk is Online Monitoring with Optical Spectroscopy at Savannah River. I'm going to talk about first, because most people that I'm talking to here are coming at this through an engineering background, and my background is in chemistry and physics. I talk a little bit about how I got to where I am, and then talk about, in sort of broad terms, what it is that I do and what it is that the group that I belong to, the online monitoring group, does. It's a variety of instrumental techniques applied to a variety of different applications across Savannah River. Then I'll go into a little more detail about two projects that I've worked on in recent years, one of which is absorbance spectroscopy of plutonium in different oxidation states in our HB line facility. I'll talk about some Raman spectroscopy that we've more recently done for tracking the dissolution of nuclear materials in H Canyon. And then very briefly talk about some projects I have going on right now, sort of all on one slide, some X-ray work, some other Raman gas analysis work for our tritium customers. I'll talk a little bit then about what it is to be a scientist trying to get projects to work in a facility. It's a big deal to cross the gap between having something work in the lab and having it work in the facility. So I'll highlight some of the things that I think about that I think are helping me be successful in doing that. And then the last little bit, I'm going to talk about a new opportunity for working in plutonium processing. This is a new project, a new program that Savannah River is involved with, along with Pacific Northwest and Idaho National Labs. So how did I get here? So my career it's a little bit of a hockey stick. It's not a completely zigzaggy route like some people take, but it definitely is not. I'm not going in the direction that I started with when I started on my chemistry pathway. And that pathway was first, as I mentioned, in chemistry and physics. I was very much in the direction of doing basic research on spectroscopy of small molecules and small molecular complexes that were formed in supersonic expansions, so studying van der Waals complexes and things like that. Lots of spectroscopy, but I realized the more I got into it that when people asked me what I wanted to do, I basically was saying, well, we're kind of validating quantum mechanics, and we're measuring these small things that I found increasingly difficult to justify or to motivate people when I talked about why they would want to be interested in it. So although the work was going fine, I decided I really did need to take a break. Worked for the Environmental Protection Agency for a few years, did no spectroscopy whatsoever. But then realized that while I liked the subject matter of spectroscopy, I found that another way to do that and still do something that was more interesting and more applicable to people was to go into analytical chemistry, which I always thought of as essentially applied PChem. So went off to grad school at Wisconsin, go Badgers. Did work in nonlinear optics, which you wouldn't think was necessarily related to analytical chemistry, but we concentrated on the ways that could improve detection limits and that could improve the ability to selectively detect one particular species out of a whole mixture. So that led into being able to go off to some place where analytical chemistry could be put into practice. And that turned out, fortunately, to be Savannah River, where I got hired on directly out of grad school, which was another stroke of luck, into a group that was doing process monitoring. And while I've been involved in different projects with different technologies over the years, that's essentially what I've been doing ever since. So what do I do? Try and move my little screen here. Well, I don't think I'm going to be able to do that. All right, so what do I do? My work involves several different general applications: nuclear waste cleanup and nuclear waste processing. The stuff I'll mainly be talking about today, work in H Canyon and HB line. Efforts for preventing nuclear proliferation, and then developing new energy sources, which is related to the tritium work. So, as you would expect me to say, I do that by doing online process monitoring, specifically spectroscopic methods. And to carry that out, there are a lot of different tools that I work with: UV-Vis, Raman, different vibrational spectroscopies, X-ray spectroscopy, chemometrics, process chemistry. Everything that I've listed in the blue there is all stuff that I picked up after I started working at Savannah River. So one thing that you should definitely expect, regardless of what your background is that you're not, if you continue on the path of working with nuclear materials or working in the national lab environment, you're certainly not going to come into the position knowing everything that you need to know. And who do I work with? It's a wide variety of people, from my fellow chemists and engineers to colleagues who do different types of research, including actinide chemists, other types of scientists, and then folks in the facilities, plant engineers, operators, technicians, all of whom have different takes on things, and all of whom need to hear information in a different way. And towards the end, I'll be talking about how I interact with those folks as part of what I do on a daily or a weekly basis. So our group, I'm not going to go through everything here, but our group does a lot of different stuff. We have different optical spectroscopies, lots of statistical analysis. We worry about things not just like how do you take the signal from these analytical methods and turn it into chemical concentrations and other bits of actionable information, but also how can we make these instruments behave in a way that they're very stable in the process environment. We're not often in a case where we can go and calibrate the instruments every time we need to. So they need to be reliable and rugged for extended periods of time. How we interface those instruments with the facility involves all of this kind of stuff, both hardware and software. I'll talk about some of these again, but basically the main things I do is look at different ends of the periodic table, either the heavy stuff or real light stuff, and show you some examples of each of those. Currently, as I mentioned, I'll be talking about some of this. Other things I won't necessarily mention, we'll be looking at lanthanide dissolution kinetics using Raman and X-ray analysis and some UV-Vis. That helps us understand some of the chemistry that's behind flow sheets for nuclear materials processing. Our group is also supporting some work with Mark 18 fuel, looking at ion exchange separations of all of these different species. All right, and we do that both in the facilities and in supporting the colleagues in the laboratory. So, most of my audiences don't really know much about H Canyon or HB line. You guys probably do a lot more, so I won't go into it too much, except just to point out that this aerial shot, H Canyon, is down over here. HB line is back up behind where I have everybody's picture. So if I ever do get to, I don't think I can reduce that. Anyway, all right, I'll just skip over that. Let's see here. So we, H Canyon, HB line, they're only operating production scale, radiologically shielded chemical separations facilities in the US. So we are still actively taking fuel that we have from different campaigns and dissolving it up. And that work is slated to go on for at least the near foreseeable future. Because this is the only such facility, there's always to look out for new campaigns to keep people active and to keep nuclear materials from just accumulating. Our process is based on a modified Purex process, which is an extraction process based on aqueous and organic phases, and it uses mixer settlers to do that. The canyon, depending on whether our fuels are aluminum or stainless steel clad, will have different dissolution technologies. It's been mainly chemical, but one of the projects that's ongoing right now is to start up an electrolytic dissolution process to look at to be able to dissolve stainless steel clad fuels. That should be coming online in a few years. We separate out all the isotopes, and then depending on which we want to be looking at, uranium gets further purified in the canyon, and plutonium, or in the past, neptunium, has been purified in HB line. So on the right's a little close-up of the entry to the HB line. This is mostly the same, but I just wanted to show that the examples I'll be talking about occur at 3 different places in this schematic of the process. Looking at dissolver and separations in H canyon, and then in HB line in the purification step, the separation of plutonium from the liquor on a column separation. We look at that, and then we also look at the solutions that are sent back to H canyon for further reprocessing. So, looking at purification of plutonium in HB line. The process for this is on a cation exchange column, where solutions are brought in from the canyon, adjusted and taken up to a high acidity, 8 molar nitric acid, flow through this, through a little flow cell that we have to monitor solutions, and through this column where the plutonium nitrate species are in their +4 oxidation state, are selectively absorbed onto this column, and the waste flows through and goes back to the canyon. After the column is loaded, we then elute the material off of it with a low, comparatively low concentration of acid. It flows through in kind of schematically in this process, where the low acid is just sequentially pushing plutonium off the column and putting it down, so that by the time it gets to the end of the column and through our flow cell, we've got a very strong front of plutonium of high concentration coming through. When we detect that the plutonium is coming off in that way, we automatically activate a cell here, or rather a valve that will, instead of taking the solutions from a recycle, it'll push it off to a product tank, where after further adjustment, the solution is then evaporated and converted to an oxide form. So it used to be back in the old days when this process was being monitored, they had just a sight glass up here. And as soon as somebody was looking through the glove box where all of this is located and they saw it turning dark, they sent a signal out and somebody else would reach in and turn the valve manually. Over time, the process has become more and more automated, and the engineers wanted to get more and more information and more control out of the system. So whereas originally we had set things up with optical fibers to just look at stuff getting dark, then we started looking at more conditions where the plutonium spectroscopy became more and more complicated. So one example of this is that if you look at plutonium in its +4 oxidation state, and you look at its UV-Vis absorbance spectrum over a variety of different acidities, you'll see that the spectra do change. I mean, very qualitatively they're the same, but for example, if you look at this series of peaks over here in the high 400 nanometer range, at high acidity, you've got rather broad peaks that correspond to a combination of several different plutonium nitrate species. But then when you get to low acidity, some of those higher nitrato complexes go away, and you just have very sharp a single very sharp line that's due to PU 4 plus without any nitrates on it. So the thing is, with a spectrum like this, if you just want to monitor the absorbance at one or a couple of wavelengths, it's going to be very hard to get consistent measurements of plutonium concentration if your solutions are going to have a variety of different acidities. To further complicate things, if you have plutonium at low acidities, below 1 molar, maybe 0.4 molar or less, what will happen is this disproportionation reaction, where plutonium in its 4 state will change to a mixture of that 3 plus and 6 plus. The 3 plus and the 6 plus have different absorbance spectra. They're different colors. And if you were trying to make a measurement where you were looking at, for example, trying to do a baseline measurement over here and an absorbance measurement over here, well, you're getting an anti-conservative negative bias on your measurement, because not only would the 4 plus peak be going down, but your baseline for the 3 plus peak would be going up. So if you want to get a consistent measurement with all of these conditions going on, you have to use all of the information, or much more of the information that's available in the spectrum. I'll get into how we do that in a moment, but first let me take a detour and tell you about how we made our instruments more rugged by doing something special with diode array spectrometers. Now, if you've done enough absorbance spectroscopy, you would know that kind of the gold standard, if you will, for getting consistent measurements is double beam absorbance. And what that entails is you take your light source and you split it into two, and you have one arm being a reference arm that would go through some kind of a, like say a blank reference solution and then be detected. Whereas the other arm would go through the sample and what you're trying to measure. When you ratio the signals due to those two arms of the measurement, you're getting rid of any variation in the light source as you go along. And that reduces the baseline that you have. What happens though with a diode array spectrometer, you normally would run that in a single beam mode, where you're able to measure all of the wavelengths of light simultaneously, but you are susceptible to any differences that occur when you measure your reference sample and then go and measure your sample spectrum at a different period of time. This is particularly problematic when you're trying to make a measurement in a process where it could be a long period of time between when you measured your reference and then when you're making an actual sample measurement. So what we've done is developed a double beam diode array spectrometer where we do the splitting of the light and then project it, each reference and sample arm separately onto an individual array unit. What makes this difficult potentially and required us to do this extra bit of development is that the pixels on the diode array spectrometer don't necessarily, in fact usually won't line up with one another. And so we've done a lot of work with wavelength calibration where we have entrained some light from a xenon lamp arc source to serve as internal wavelength standards. And we do real-time calibration of the wavelengths of each pixel for each individual spectrometer based on how they match up with how these peaks line up with the reference lines, and then do interpolation so that we know when we think we're measuring 600.02 nanometers, for example, on one unit, we know exactly where 600.02 nanometers is on the second unit. And we know when we do the absorbance measurement by looking at the ratio of the intensities of those at those two wavelengths, we know we're actually comparing the same wavelengths. Similarly, we've done a lot of characterization of the intensity response of those detectors so that at both high intensity and low intensities, we're doing proper subtraction of any dark noise, we're taking care of any second order corrections, we're looking at any compensating for any differences that would arise from a nonlinear response at high intensities, and are able to get very accurate absorbances compared to NIST traceable standards even above 2 AU. So we've got over 2 orders of magnitude of range available to our measurements, and we're able to measure wavelengths quite accurately. So all of this, we call it a virtual spectrometer. And what we found is that when we take multiple instances of this unit, all of which are calibrated to either natural standards, which are the frequencies or wavelengths of these lines, or NIST traceable standards in the case of intensity, we can then go and make a multivariate calibration on one instrument and transfer it to other instruments without any kind of a calibration transfer scheme. We've basically taken all of our effort and poured it into making the instrument seem as close as possible, as identical as we can make it within the tolerances or the uncertainties of these standardizations. And what the graph down here shows is that most of the variation, when you compare the prediction error for 3 different instruments with a model that was developed for just one instrument, most of this scatter comes from scatter of the calibration solutions themselves. That the spread of these different values, by and large, is comparable, if not better, to the spread of values that we get, the spread of errors that we get just in total. Okay, getting now to the chemometric side of things, we further are able to handle all of those different sources of variation that I described earlier through what we've called a piecewise local partial least squares modeling system. So the basic idea of this is that I described how you have different nitrato species of plutonium that can be present depending on the acidity. You also have different oxidation states of plutonium that can form under some acidity cases, but not others. I also didn't mention temperature, which is another factor. So if you were going to try and do a multivariate analysis model that encompassed all of these different conditions, one way you could do it is to make a big global model that tried to capture all 7 or 8 or whatever different sources of variation at the same time. But the problem with doing that, in our case, is that not all of those different sources of variation are going to be present simultaneously. And so, in essence, for any one set of conditions where you're trying to make a measurement, you're going to end up overfitting your results. So instead, what we've done over here on the left is set up a scheme where, based on, well, I'll start in the middle, and I'll explain why in a sec, but based on either the acidity and then the apparent oxidation states that are present in the solution, we narrow down the cases so that we can selectively pick a model that only incorporates, only tries to take care of the certain sources of variation that we expect to be present for those solution conditions. So basically, say for low absorbance, and I picked this because we're looking at this very sharp, relatively intense peak out here, we still don't want to use that if its absorbance is too high and outside our range. So let's say that that's good. We pick the acidity. If it's high, we would expect, say, maybe just the more highly nitrated plutonium species and only in the +4 oxidation state to be present. And we made a calibration model that just assumed those species. You can go through the same arguments for medium, and then for low, we do another absorbance check that's more specific to plutonium-6, and then use the appropriate models to predict, in this case, not just the 4, but also the 3 and the 6 plutonium concentrations. Where that comes into play would be if we compare a number of solutions that we got from the process, an HB line in this case, at different light levels getting through different baseline offsets and lots of noise and stuff like that that occurs due to turbulence in the stream. If everything is just really nice and smooth and we've got high quality signal, then the predictions of that global model and of the one particular local model that applied are essentially identical. But what happens in the global model is that because you've got more principal components that you're trying to use to predict the spectrum, you end up having lower signal to noise available to you when you're getting out to those fifth, sixth, seventh principal components, where you're really trying to narrow down and hone in on the measurement, the concentration you get out. And so you see, as you get more and more noisy, the amount of signal that gets associated with the noise goes up, and so your prediction goes all over the place. In comparison, the values that we read out with the local model, with the appropriate local model, are comparatively invariant, even with some relatively low quality spectra. So we see similar results for that at different scenarios, at different parts in this analysis scheme. And that has helped give much more stable and robust measurements for our instrument compared to a less picky model. Okay, so those types of schemes, we've applied them in two different places out at Savannah River site. I described the use of it to measure plutonium in three different locations out in HB line, and I'll say three different locations because they have two of these columns out there and one waste stream. And in doing so, we were able to have a much tighter uncertainty of the plutonium concentration coming off of the column, and then we're allowing them to change when they reclosed off this valve, and they didn't have to dilute the plutonium concentration so much inside of this product tank, and that helped increase their processing throughput by a factor of 2 to 3 by not having to drive off so much water. We've done something similar out in H Canyon, where spectrophotometers were identified as one of several ways that they could enable a 50% increase in their yearly baseline processing rate. And we installed these spectrometers to measure uranium at 5 different locations in the second uranium cycle. Let me see here. I'm going to stop for just a minute. I see some, oh, I can't get to that either. Let me see if I can turn off my pointer here. Okay, now I can, okay, I can do that. And I'm just going to see if there are any questions while I'm at a natural stopping point. Okay, so I'll just stop for a second because Kevin's asked if there are any discontinuities resulting from this type of modeling. And yes, that's certainly something that we discovered in our first iteration of this. One way you can go and get around that is to potentially look at the model results from several of those different pathways. Once you've established the models, it's relatively quick to work your way through that little algorithm. So you could average the results of adjacent models, if you will, in that little range of different solution conditions where you're close to the border where you would invoke one versus another. But that's something that we've definitely seen during evolutions, where the curve would be going in a certain way, and then there'd be these little hops that would occur, and they correlated with how we saw how the algorithm was going from one branch to another branch.
Very typical. I was just curious. There are different ways to handle that, certainly.
Yeah. Then the second one, are the principal components typically meaningful from a mechanistic or first principles perspective? In general, the answer for this type of method is that they are not, because the components are based more on just the figuring out what the maximal variance is, and then going in an orthogonal direction and resolving the maximal variance in a different direction. If you wanted to get results that were closer to physical reality, you would use a different type of technique. A typical one that's used is called multivariate curve resolution, right, which is essentially just trying to solve multiple linear equations simultaneously. So what you would get in that case would be essentially trying to estimate what the spectra of, say, PU3, PU4, PU6, and PU4 and its different nitrato complexes, what those would intrinsically be, and then how you would have to weight them to reproduce the spectrum that you get.
Right.
So
again, and it's not just your principal component. It's almost always in principal component analysis you run into the same issue. So it was not meant to be critical. It's pretty endemic of using principal components.
Oh no, that's absolutely right. I think it's worth mentioning because that's not something that's always realized, that people always realize when they start to get into this. So
right. Like neural nets being nonlinear regression. People don't like to talk about it.
Yeah. But you do have to be careful about what you claim based on a principal components type analysis.
Absolutely. Thank you.
Yeah. Okay. All right. So let me move on to the second thing I'll talk about. And I've showed this slide before. And again, where we're actually looking. Laser pointer back on. This time we're going to be looking over here at the dissolver. And we're looking at trying to dissolve different types of nuclear fuels in our facilities. Basically, the dissolver looks like what's shown over here on the left. They actually have a little parking lot of all of these different dissolver components sitting outside of the facility, and you can walk around and marvel at how tall it is and all that stuff. But basically, the fuels that we look at are either real long and skinny, and they go inside of these inserts that are lowered down into a well that's filled with nitric acid, or they're relatively short and squat, and you've got two concentric cylinder shapes that go into a different shaped insert, where the fat one goes in here, skinny one would go in here if it was in the picture. And then it's slightly different. This is directly, slightly different because these fuel elements are shorter. All of these, both of these species, both of these cylinders are submerged into the nitric acid all the time. In this case, because everything is so tall and thin, these fuel rods actually sit above the nitric acid in the fuel, and then as they dissolve, they kind of work their way down the columns here. So all of this is at elevated temperature, nitric acid everywhere. It's not something that you're going to expect to be able to look at directly with some kind of a camera once the dissolver is all closed up and it's operating. So if you want to have some kind of way to monitor the progress of these of the dissolution of these fuels, you have to do it indirectly. And one way that you can do that is by monitoring the dissolver off gases. And we can, some chemistry here just to show that the species that are liberated include different NOx's. You also have production of nitrogen, you have production of hydrogen, and oxygen does get used up during the process as well. We've chosen to use Raman spectroscopy to look at these gases as opposed to infrared because we are particularly interested in tracking the production of hydrogen, which not only involves, tells us something about the chemistry, but also lets us know something from a safety perspective. You know, is the hydrogen being destroyed as it works its way out the column? Do we have to worry about flammability concerns in addition to other operational issues? Another reason to choose Raman for this technique is that we have a much better potential for access, where we can use optical fibers, which are highly transmissive in the visible, but you can't really have any special materials that are going to run the tens to hundreds of meters that you would normally want to have to separate your equipment from the process if you're going to be looking at it in the infrared. What we give up when we're going with Raman as opposed to infrared is that sensitivity of Raman is comparatively poor to IR. In this case, we don't necessarily, a couple of things that are to our advantage for Raman. We when they run this, they're basically not trying to turn any knobs or change anything like temperature or pressure in the vessel. They just run it. They want to know when it needs to be done. So we have time to take the longer measurement and compensate for that lack of sensitivity. Also, we're not really looking at ultratrace detection of gases. We're looking for signals that will indicate when they're done or done enough. Done enough in this case being that they have finished enough dissolution that they can go and put in the next batch of fuel into the same pot of dissolver liquid, and then proceed without having to knock out pieces or otherwise have interferences that keep them from being able to shut the lid on top. Typically, the facility will dissolve 5. For the MTRs, they'll dissolve 5 of these in different batches at any one time before they take the solution out and continue processing, or they'll dissolve 3 of these high flux reactor types. So they're trying to load in on top of what they've already dissolved in either case. And then we also went with Raman because we'd used Raman to monitor off-gas and laboratory flow sheet studies. So we knew that Raman would be capable of detecting these different species to the concentrations that were going to be of interest. In developing this, we got a break. Our friends in the non-proliferation group in SRNL had developed an analytical trailer that was parked outside of some off-gas lines next to H Canyon. They've got different instrumentation for their own purposes, but they let us go in and set up our Raman instrument inside the trailer and get into one of their lines. So in this case, where we're demonstrating the feasibility of Raman, looking at real samples, we didn't need long fiber lines, but those fiber lines we could certainly make them longer and they'd get the same quality results. So over here on the schematic, the star is where the trailer is. It's outside of the canyon wall. All of our dissolution is going through here. The gas comes out, goes through a condenser that helps recover nitric acid, goes through a silver nitrate reactor. This actually helps strip out iodine that's produced as a byproduct of the nuclear materials. Go through some sand filters and stuff like that, and then out the stack. So thinking about how you're going to implement this and what it is that's different about a laboratory instrument versus or doing this work in a laboratory environment. Lots of NO2 is there, and what we found is that if we excited at 640 nanometers, kind of an orange color, that we got adequate sensitivity, sure, but we could get more sensitivity if we excited at 532 nanometers because that was resonant with some absorbances of NO2. So if you looked, we'll pick a line. We'll pick this line. If you look at comparable concentrations of NO2, you'll see that the lines indicated here with the asterisks are much stronger with the resonant excitation, even with a much shorter excitation time when we excite at 532 versus 640. But you'll also notice that there's a lot more background as well. So trading off one versus the other, is it useful to you to have this higher signal when you are looking at when you're trying to pick it out of a bigger background? As it turns out, what we're really interested in is not so much how much is coming off at the peak, but how much is coming off at the tails. And so in that case, having the higher NO2 concentration and having this higher background tended to obscure the weaker signals that might come out of these other gaseous species if they were present. So ultimately, what we've decided to do is to go with the 640 nanometer excitation and give up a little bit in terms of sensitivity in favor of being able to see more species. Some other things we've done, we do some corrections for drift of our wave numbers of our Raman shifts. That trailer is air conditioned and all that, but it still is it still does vary by 20 or 30 degrees in there, and so you do get these diurnal variations in the peak position just due to the spectrometer shifting. But we're able to correct for that, and what I've shown up here is in our modeling where we're looking at percent N2, just we're doing this with air in between runs. Basically, all of this variation is just we're trying to fit to a peak we expect to be at a certain position, and as that peak, what we actually measure goes on and off resonance with our little where we expect it to be, the solution, the fitting goes all over the place. But when we do the corrections, we get very, very consistent results despite the changes in temperature. Then, we had to contend with having the right materials in there because this gas coming through, NOx is very corrosive, of course. So we actually went through a period where we were starting to get leaks because we were corroding the heck out of things. Fix that. Should have realized it the first time, but live and learn. Then a little chemistry surprise, which was fun, and a subject for a little side project, trying to understand what happened to the gases that I showed earlier, because in the end, all that we ended up seeing was NO2 and not any of these other species. So that led to an investigation of the chemistry of the silver saddles, stuff like that, and that's come out recently. But I won't go into that, but instead concentrate on the analytical chemistry aspect, where indeed that we showed that we were able to track NO2 and have that be a good proxy for dissolver activity. All of these little numbers here on this curve, this time trace of NO2 coming out for one of the dissolutions, we knew from the logs of the process when they would do certain things, like turn on the heat, inject a mercury catalyst, turn off the heat at the end. It turned out that in this particular case, they hadn't actually fully dissolved their fuel, and they had to turn everything back on. So we could tell when they did all that. We could also get reproducible measurements at concentrations down to 1/10% to 1/20% of NO2, and see where they had dissolved, they had turned off the heat. They did their probing, which was actually as simple as sticking a very long stick in there and seeing how far down it went. Saw too much that was in there, heated it back up, dissolved it some more, started to get a consistency in their in the output, measured it again, it was within their limits and they could move on. So we've been doing some work, and we're going to be continuing to do some work to be able to take the absolute levels and the slope of change of these levels for both the different types of fuels, because they're different geometries, they're going to have different dependencies, and turn them into a go, no-go indicator, where if they get a consistent, well, we've called it red, they get a consistent reading that says you still need to keep going, they can keep dissolving even when they get to what they think their endpoint is based on their process history. We can encourage them to go and keep heating for another hour or two, maybe get it down even lower, so that they can avoid this process of cooling it down, probing it, sealing everything back up, heating it back up again, and then dissolving some more. So this has a lot of potential for them to be able to save time and money in their processing by avoiding processing errors or hiccups, if you will, in their dissolution. Other projects that we're working on, up here we've got a project using X-ray absorbance so that we can measure plutonium and uranium in the dissolution plots for the electrolytic dissolution project. We're not using regular UV-vis absorbance in this case because we're also trying to measure in what are opaque solutions with lots of stainless steel transition metal products in there. Fortunately, X-rays are more transparent with respect to those other species than UV-vis is, and so we're able to get actually even fairly low concentrations down in the maybe 0.1 to 0.3, 0.5 grams per liter of these uranic, transuranic species. And we've done a lot of work with, again, developing instruments and doing data analysis that would allow us to resolve different interferences that do occur. I mentioned a little bit of work looking at tritiated gases. Because hydrogen, again, does not absorb in the infrared, if you want to track isotopic distributions of things like hydrogen, you would want to use Raman. Again, Raman is not very sensitive, but one way that you can increase the sensitivity is to confine the gas to some kind of a reflective waveguide. And if you can use that as a way to effectively increase your sampling volume, and then capture the Raman scattering that gets propagated back along the waveguide and gets radiated out, then you can increase your sensitivity. These are some preliminary results here where we're just looking at air, but we're able to see the nitrogen 14, nitrogen 15 isotopolog of nitrogen in air, different row vibrational lines, and so far 400 part per million or less, however much CO2 there was in the atmosphere that day, we can see those signals. So this project is trying to further increase these detection limits, and we're trying to package this in a way that's going to be tritium proof. Tritium, because of its beta decay, has some materials incompatibilities that you don't see if you're looking at other types of analyses, such as a natural gas analysis, which is where this technology has also been used. And then just for fun, that I will mention that I do other things like look at changes in glasses that would occur during exposure to radiation. In this case, looking at how changes in this borosilicate network may have occurred under exposure in this for nuclear waste glass simulants, and what the implications might be for long-term storage of nuclear waste. Okay, before I hop into the next thing, I'll stop again and look at the questions. I can get the pointer off. Okay, all right, that's not a question. Thanks for the nice message.
May I ask a question?
Yeah, go ahead.
I apologize. I was just typing it and you were moving on, so I apologize. Even though we don't take credit for the glass in the disposal environment, so are you going to help us convince people to actually take credit for the waste form when we dispose of things like high-level nuclear waste glass? For those of us who spent 15 years making sure it would be durable?
Okay, so I guess I could say that what we have seen with the levels that we'd exposed the glass to, that there really weren't any structural changes.
Which we've done similar tests, and it would be unexpected that you would see much in the way of structural change.
Yeah, but we've gone ahead and at least to confirm that.
That's great.
Like I just showed the Raman, but we've used a variety of different techniques that are all more or less invariant to these different types of glasses, or to the different exposures.
I understood. Yeah, thank you.
Okay. So again, as I've been saying, that it's one thing to have these instruments developed in the laboratory, and it's another thing entirely to have them work out in the field. And so I've highlighted what I think are 4 key things to strive for in trying to get instrumentation to work out in a nuclear facility. The first, and really the first 2, correspond to the general idea that you have to convince the folks who operate the plants that they want to have your instrumentation out there. It's usually not trivial to put the instrumentation in. It's an investment for them in time and in money. And if you go swanning in saying, oh, I know how to solve your problems, and you don't really develop solutions with them, you're just going to have a much lower likelihood of success, either in terms of their letting you do it, or that you're able to understand all of the different problems that could crop up. So I've always found it important for it to be a collaborative effort and to serve as a broad-based technical resource, because you can be a specialist like I am with spectroscopy, But if you're a resource for them where they could ask you a different type of question, if you don't know the answer, you know how to find them the answer, get them talking to the right person, they learn to trust you in a technical sense. And that just makes it a little bit easier for you down the line. Likewise, building relationships at the staff level, it's not just management, but also talking with the folks that you're going to be working with, whether it's operators, whether it's the facility engineers. They can tell you about the little tricky things, like what it is, what's involved when you're sampling solutions from the tanks if you're doing an at-line analysis. You can work with them to develop solutions and become part of their community. Also, if things go wrong and you're there to support the equipment that you put in, they know that you're not just kind of fly-by-night, that you're part of their team to make the process run smoothly for an extended period of time. As is the case with anything else that the facility is going to be doing, it's very much a project to put these things in, which means that you need to have a good schedule, what your tasks and milestones are, some idea of what it's going to cost. It's a very uncomfortable situation to be asking for cost overruns to be covered. So, understand what you're trying to do. Try not to have it be a science project at the same time as much as you can. And try and keep your scope under control. That's good advice no matter what kind of a project you are engaged in where you've got a customer paying for it. And then things like, we could go and display spectra all over the place if we wanted to, but really the engineers want to know a limited bit of information that's going to facilitate their decision making. So what is the concentration? Is the instrument actually working? Do you have onboard diagnostics that are going to help give them that assurance? If something's wrong, how much do you want them to be troubleshooting versus what they need to call you for? So understanding that process, helping them define what type of ownership, what roles of ownership they can have versus which ones you need to be available for are important things to work out as well. So some examples of the latter. When we hand them an instrument, we're not just handing them an instrument, we're handing them the instructions. We're working with the folks who write the procedures out there to make sure that when they translate it to an operator procedure, that they're capturing the right things. Again, we get their opinions on practical considerations. For example, I mentioned those NIST traceable absorbance filters for the spectrophotometers. In our first iteration, up here on the top right, we had a situation where they would open up the cabinet and slide out a tray and put the absorbance filters in back here. It worked technically, but that was much more of a process, and you ran the risk of you removing the fibers when you're sliding this around and all that. It just really wasn't very as efficient as it could be. So we re-engineered where we had the fibers and where we had our cuvette holder so that for our second iteration out in the canyon, we basically had the same little slot, but it was on the front face of the instrument. So they could take their standards and put them in one at a time, follow a procedure that was step-by-step on this touch screen, and they didn't have to open anything up, and that worked a lot better. Similarly, when they're doing that calibration, we basically had a step-by-step procedure that would prompt them to put in a certain type of standard, and then it would do its measurement, tell them when it was done, tell them whether it passed or not, and then they could move on to the next one. So it was a very seamless and easy thing for folks who are not trained spectroscopists to operate a spectrophotometer. Again, we have a lot of information, a lot of diagnostics that come out of this. So, so we made sure to do things like if we had a simple display, or if we had a display that was potentially complicated, we would color code it. Green is good. If it was yellow, it was potentially a concern, but it might still be working. If something was red, call the lab or do this or do that. Other things, as we mentioned before, looking at the transitions between different arms of this of this decision tree, we would sometimes have edge cases or discontinuities, and we would have to work through either trying to smooth those out or explain why they were comparatively inconsequential. But those things exist, and a curious process engineer is going to say, hey, what is that, and do I need to worry about it? So all of these operational issues are things that you get to worry about and get to incorporate in your instrumentation. So finally, the last thing I wanted to briefly talk about was a new program that is being carried out by several national labs, ourselves, Pacific Northwest, and Idaho National Lab. It's called Athena, which I've been told is not an acronym, and it's just for Athena, the goddess of wisdom. The idea is essentially that the knowledge behind, the operational knowledge behind nuclear materials processing, plutonium in this case, there's a similar one for uranium, that is starting to disappear from the complex. People are getting older, they're getting retired. We need to bring in the next generation of folks who are going to pick up all of this information, preserve it, and then take it forward with further development, not only for domestic processing needs, but also as part of non-proliferation efforts. So this effort covers all of the areas, essentially, of plutonium processing, all the way from receipt to precipitation, but it's in particular focusing on starting with head-end processing and going all the way through ion exchange. So as I mentioned, knowledge retention is a big effort, and we're looking at workforce development. And so we're looking at all ranges through the career stage, from early career up through mid-career and late career, in especially the latter, in promulgating and passing on this information. So we've got lots of opportunities for postdocs to get their feet in at different national labs, and we're looking at this both in terms of what do I want to say? We're looking at all areas that would go underneath that umbrella. So not just online monitoring, but also flow sheet development, process modeling, and data analysis. These are all, just as they are in the complex now, multidisciplinary teams. And I think, at least at this early stage, we're doing a lot better with respect to developing multi-laboratory teams, as opposed to having information get siloed between the different labs. So very exciting potential opportunity. If it's something that you want to find out more about, feel free to shoot me an email. I think my email is on the distribution for the talk. If it isn't, I'm sure that you can get it from any of the organizers. I'm running out of time here, so I'm going to skip over this and just highlight that there are a couple of examples. This is from PNNL, where they have combined information from Raman spectroscopy of uranium, both Raman and UV vis of uranium, plutonium, and nitric acid in a bank of contactors, along with physical measurements from flow rate, density, and Coriolis meters, and have been able to track the concentrations of different species within the separator, and it corresponds very well with grab samples. And then again, us at Savannah River looking at plutonium measurements. And we've also done some work, which was on that big sheet at the beginning, looking at, we're going to be getting to UF6 as a isotopic measurement for uranium, looking at its vibrational spectroscopy inside a gas cell using a tunable diode infrared laser. They've been doing some work with molybdenum as a substitute. So with that, it looks like my last slide. So thanks for listening, and I am happy to answer any questions. I see a 1 in the chat, so I can hop on that first. Oh, okay, someone else who had to leave. All right, any questions that I can answer?
Thank you very much. So any questions?
We tend to let the students try to go first, even though I cut in
Yeah.
like 3 times when you were speaking.
I have a quick question, if that's okay.
Yeah.
Thank you for your talk, Dr. Lascola. So going back to the piecewise PLS model that you were showing kind of like near the beginning of your talk, for each of those sub models, I guess local models or whatever, is the main difference between them the training data that I guess is building the model? Like, is it local data around whatever that set point is? Is that how the different models are constructed?
Sure, and that's the way that we did that. We took subsets of the data set for the calibration set for the global model, and then made the individual models out of those. So that is another that was a bit of a concern too, because we I mean you don't have an infinite number of samples. So some of those models turned out to have fairly low numbers making them up. Part of the partly as a result of that, that encouraged us to overlap those regions in terms of what samples were included in the calibration set. So that did do a little bit towards addressing the discontinuities that we've been talking about between those different pathways.
Okay, thank you. And I guess to follow up on that, when you have the decision-making process for choosing the submodels, like if it's like a certain acid regime or different things like that, is that informed by the spectra itself, or is that like a pH probe is telling the model which submodel to use?
It was informed by the spectra. So you can actually, we actually had models for predicting nitrate. And based on that, we were able to do the partitioning. Okay, so essentially, yeah, I mean, I mentioned how for that one set of peaks out in the high 400s, around 500 nanometers, your shape is, the shapes of the peaks are changing because of the overlap between the different nitrato complexes. You can essentially, if you normalize those spectra, you can do PLS on that and turn it into kind of like a shape recognition routine rather than a like strictly a quantitation, and then correlate the shapes of the concentrations.
Okay, thank you.
I think I have one quick question. Again, thank you, Dr. Lascola, for your talk. I was just wondering, so again, going back to that, the UV absorption spectra that you were showing for different oxidation states of plutonium, like we could see like in, I think that the 400 or the high 400 nanometer range, like it had like a non-linear behavior, right? Like it was, the peak was essentially shifting, like there was a shift, and then also the shape of the peak was changing. So is there a particular reason that still like you guys decided to do like a linear regression model rather than a non-linear one?
Okay, so it is those, if you fixed the acidity of a solution and then just change the plutonium concentration, the absorbance spectra would be linear over a wide range of plutonium concentrations, which included all of the ones that we would encounter in the process. I mean, if you went up to, I'm going to pull a number out of the air, if you went up to 100 or 200 grams per liter or something like that, I don't really know where it is, then you start to change the equilibrium distribution between the different plutonium nitrate complexes. So, I mean, you could just imagine if you had a fixed amount of, at a fixed acidity, and you start throwing in more and more plutonium, you're going to not have as many nitrates to go around. And so you're going to start favoring more of the lower nitrato species. So in that sense, when that kind of thing happens, then your PLS, you'll start to be nonlinear, and then your PLS will be an issue. But where we were looking at, it wasn't an issue in linear. We could use linear methods to do the analysis.
Okay, thank you.
I can't help myself, even though I'm not a student. So actually, one of the things that this is not necessarily for you, Dr. Lascola, but for the younger people on the call, and everyone's younger than I am. But when you were talking about you had your messages that were red and green and yellow, when I was first started, I was much younger than anybody on this call, and we were doing the Pu-238 interesting isotope treatment facility. And I set up this fancy board that had all the flashing this and flashing that, red, green. John Plotnick walked in and goes, I'm red-green colorblind, because 1 out of 12 men are red-green colorblind. And so when you start putting this sort of information out there to people, you have to be careful that you're talking to everyone, because a lot of people don't see that as red and green, and you have to worry about that. So I thought that was interesting. It was funny, you were talking about doing your localized models, and back in the day when I was working on the GLASS program for the high-level waste vit, we came down in exactly a different place in terms of doing global versus localized models. And we had a big debate with some of the PNNL statisticians back in the day about that. So it's interesting how you come down from really very carefully positions and come up with 2 completely different answers. But I thought that was interesting. Not right or wrong, because it's statistical and it's you're using the best technique you have. So I thought that was interesting.
Yeah. Well, I was going to point out in a couple of places here. Let's see. So in the end, behind all of this, there is a single error indicator that is tied into the facility's distributed control system. So, an operator, the rack that has all of this instrumentation is like off in the corner somewhere, and you have to walk back there to see it because it's behind some other stuff. So we're tied into their DCS with analog and, well, I guess it's all digital now, but we've got error indicators that's as simple as it's great or it's not great. And if it's not great, then they get to go back and evaluate it. So, and then in some cases, like you can see right in here, it's not just green, it's also got words, a word, it's true.
Right. Oh, that's why I was saying it wasn't specific to what you were showing. It was more a general thing where I messed up because I was relying upon the colors and it wouldn't work for 1/12 of the people. So I kind of understood what you were saying. That was more general in nature.
Yeah, well, I guess I was just pointing out that, there's more than one way to display the information, right? And so it does, address like a concern like that, which is certainly an important one.
Thank you. This is great talk.
Thank you.
But then I did a lot of statistics, so.
So any other questions? Oh. Okay, I think we're good. We are on time. So thank you very much, Dr. Lascola, for your fantastic talk, and we enjoy a lot. And so everyone, thank you for joining the seminar. We will see you in the next seminar in 2 weeks. Thank you.
Thank you, everyone.
All right. Thank you. And feel free to email me if you've got any questions.
Sure. Yeah.
Thank you.